All right. So in general, the motion of a rigid object can be quite complicated. If you just imagine picking up some object and throwing it through the air, the motion of the object would be quite complicated. It would be following some parabolic path. Its center of mass would be following some parabolic path, and the rest of the object would be tumbling, rotating, wobbling. It can do a lot of different things. You can show that no matter how complicated the motion of the object is, it can always be broken up into a couple of simple types of motion, and these are called translation and rotation. So let me just quickly explain what rotation and translation are. So pure rotation is when pure rotation, so let's start with pure rotation about the center of mass. And let's take a disk as our example. So this is the center of the disk. This is a point at the edge of the disk. Pure rotation means that the center is fixed and the object is rotating around the center of mass. So that's what we call pure rotation about the center of mass. So the velocity of the center of mass, so this is pure rotation. The velocity of the center of mass is 0, and all points have the same angular velocity, omega. All points have the same angular velocity, omega. So that is pure rotation. What is pure translation? Pure translation is when, let's just take the same disk. You have the disk like this. This is a point at the edge. This is a point at the center. If you were to move the disk from here to here without changing its orientation in any way at all, just move the disk. So this point at the edge is still exactly where it was relative to the center. That is called pure translation. So translation means moving an object parallel to itself, is what it always keeping it parallel to itself. So that is translation. It has nothing to do with the English meaning of the word translation. It's a mathematical term. So if you're keeping the object parallel to itself, so I'll just write this down. Yeah, and parallel to itself just means you're not changing the orientation of the object at all. You're just moving the object as a whole. So if the velocity of the center of mass, if we call that VCM, if you want to keep the object exactly the same orientation as it was, then every point must have exactly the same velocity, VCM. So that means that all points on the wheel the disk have the same velocity as the center of mass. So all of them have the velocity VCM, and the angular velocity about the center of mass what would that be? It would be 0, because relative to the center of mass, the disk does not have any kind of rotation. So that is called pure translation. All right, now in general, an object can have a complicated motion, and it could be a combination of rotation and translation. So we are going to look at some combinations of rotation and translation. All right, so let's start with this example on the slide. Consider this bicycle wheel. This is actually a motorcycle wheel and not a bicycle wheel, but anyway, it doesn't matter. So consider this wheel, and let's say that the wheel is rotating for some reason. It's rotating very, very fast. It's standing on the ground. The red line is the ground here. And let's say that the wheel is rotating very fast. And at the same time, it's just moving to the right very slowly, right? So what would be going on at the bottom of the wheel where it's touching the road? Clearly, the wheel will be scraping against the road, right? The wheel will be, there would be relative motion between the bottom of the wheel and the road, right? And so there would be some kinetic friction between the bottom of the wheel and the road, right? So the point in contact with the ground would be sliding against the ground. That's the most important thing to realize in this case. And this is an example of rolling with sliding. Rolling with sliding is sometimes also called rolling with slipping. So you use the word slipping instead of sliding. It's more commonly called rolling with slipping. So an example of rolling with slipping is when the wheel is rotating really fast, but it's moving relative to the ground rather slowly. Right? One example, one real life example of that is when you are spinning the wheels of a car, right? So when you're spinning the wheels of a car, you press down on the accelerator and that makes the wheel spin really fast, but you keep your foot on the brake so the car cannot move horizontally very fast. And so the wheel has to just spin in place while scraping against the road. And so there's a lot of friction between the wheel and the road, and that causes that squealing sound. So that's an example of rolling with slipping. Okay, another example of rolling with slipping is the opposite scenario, where just imagine that the wheel is wheel is being dragged very fast along the ground, but it's not being allowed to rotate as much as as much as it normally would. So you're just dragging the wheel along, but you are not letting it rotate. You might have seen this example when if you're sitting on a rolly chair, and let's say that one of the wheels at the bottom of the chair is locked, and then when you try to roll the chair, you hear this scraping. You see this scraping against the ground. That wheel scraping against the ground. Why? Because it's not able to roll. And so again, that's an example of rolling with slipping. I'm assuming that the wheel can roll a little bit. So that's an example of rolling with slipping. Okay. So what is rolling without slipping then? Rolling without slipping is what happens when if you were to drag this wheel along and just let it roll naturally, right? So let's imagine that you put a stick through the middle of the wheel and make it act like an axle, and then you move the stick horizontally and just let the wheel roll along, and you are not restricting the wheel in any way. You're just letting it roll along. So that's the most natural form of rolling that you can imagine. So in that case, there would not be any slippage or any sliding between the wheel and the ground, right? So the point of the wheel that's instantaneously in touch with the ground would be momentarily at rest. And so that is what we call rolling without slipping, right? There's a nice simulation video over here, which we can take a look. And I would recommend taking a look at this video yourself. Okay, so this is what we just discussed. It's pure translation, right? So the wheel is not changing its orientation at all. It's just pure translation. Okay. So I don't know exactly where the bookmarks are for this. So I haven't made bookmarks, so we'll just have to watch the whole thing. This is pure rotation. So the wheel is rotating and its center of mass is at rest, and everything is rotating relative to the center of mass. So linear velocity of the center of mass is 0, but the angular velocity is not 0. So that is pure rotation. Okay. This is rolling without slipping. Notice the white curve here gives you the location of one point of the wheel. Notice that one point of the wheel just keeps going up and down, and so this is rolling without slipping. And here are some examples of rolling. This is still rolling without slipping. Okay, so we are still rolling without slipping. Interestingly, the curve traced out by the wheel, by that point of the wheel, is called a cycloid when it was rolling without slipping. Anyway, so now we are rolling faster than rolling without slipping. So in this case, as you can see, a point on the wheel will scrape against the ground, right? So there will be friction between a point on the wheel and the ground, because the wheel is rolling a little faster than it would normally roll. And here again, the wheel is rotating too fast, and so there's slippage between the wheel and the ground. So these are all examples of the various scenarios we talked about. So please make sure that you understand all of these. Okay, now let's look at one thing. Suppose you have a disk, and the disk is doing both. It is rolling, it is spinning, and at the same time, the center of mass of the disk is moving with some velocity VCM. I want to find out what is the velocity of any point on the rim or the edge of the disk. What is the total velocity relative to the ground of any point on the rim of the disk? So the disk is rotating with some angular velocity omega, and the center of mass of the disk is moving with some velocity VCM. So I want to find out the velocity of this point, right? So that's not hard to do at all. Let's call the, okay, so to find the velocity of the point on the edge, we can proceed as follows. This point has two velocities, right? Okay, let me just draw this picture over here. So what we have here is a disk which is moving along. The velocity of the center of mass of the disk is VCM, and at the same time it's also spinning. Let's say it's spinning clockwise, and I want to find out the velocity of a point on the edge of the disk. Let's just call this the point P, and let's call this the point O. I want to find the velocity of the point P relative to somebody on the ground, and the disk is spinning with some angular velocity omega, right? So how do we do this? So what we can do is we can note that the point P has two different velocities. One of them is due to the fact that the entire disk is moving, right? So one velocity that the point P has is the velocity of the center of mass. That's one contribution to its velocity. It also has another velocity. Can you tell me what that other velocity is? So if you forget about the fact that the disk is moving, if you just think about the fact that the disk is rotating, then the point P has a tangential velocity, right? Because it's rotating about the point O. So that tangential velocity I can draw, that would be in the tangential direction. So that is the tangential velocity of the disk about the center of mass. So I'm just being very pedantic and writing V tangential relative to the center of mass, right? And so what is the total velocity of the disk? It's going to be the vector sum of these two velocities, because it's got two velocities, so these are being vector added to find the total velocity. So what is the total velocity of the point P? It would be velocity of the center of mass plus velocity of the tangential velocity of that point relative to the center of mass. And this is the formula that we have on the slide. Okay, this might seem a bit abstract to you if you're learning this for the first time. So let's look at an example which illustrates this, and then you'll see that the idea is pretty trivial. So the example is on the next slide. So the example is a circular wall clock has been flung out of the window and is flying horizontally while oriented in the vertical plane, right? So it's exactly what we talked about, except that this time it's a clock. So imagine that the clock is vertical and it's spinning and it's flying with some velocity, VCM. So we have to find, so what we're given is the velocity of the clock, that's capital V, and we are given the radius of the clock, and we have to find the total velocity of a few points marked on the clock. So let's give it a try. So here's our clock. This is the 12 o'clock point. This is the 3 o'clock point. This is the 6 o'clock point. Okay. So let's see if we can find the velocity of the 12 o'clock point. Remember that the clock itself as a whole is moving with some velocity, capital V. That's the velocity of the clock, and the clock has a radius R. Okay, now let's find the velocity of the 12 o'clock point. So the 12 o'clock point has two velocities. One comes from the fact that the whole thing is moving with velocity V. So one velocity is just the velocity V. Another velocity that it has is its tangential velocity relative to its center, right? What is the direction of the 12's tangential velocity relative to the center? The answer is it's just going to be in the tangential direction. So its V tangential would also be in this direction. And we just saw that the total velocity would be the vector sum of these two. So these are both going to be in the same direction. So we can write V, okay, so we're just going to use our equation right here. V total would be V center of mass. I'll just write this again. V tangential center of mass. And I'm just going to use strict vector notation. I'll just assume that there is an x-axis pointing to the right and a y-axis pointing upwards. So the velocity of the center of mass would be I hat multiplied by V. And the velocity, the tangential velocity relative to the center of mass would be also I hat multiplied by V tangential, because they're both in the I hat x direction. And what is V tangential? It's just going to be R omega. So it's going to be I hat V plus I hat R times omega. So it's I hat V plus R omega. That's the total velocity of the 12 o'clock point. I'll just write that as V12 for short. Can you do V3? The total velocity of the 3 o'clock point, let's just look at both its velocities. So it has one velocity in the tangential direction, and it has another velocity in the, what is the direction? I'm sorry. It has one velocity in the same direction as the center of mass. That's the one that I just drew. That's the v. And it also has a tangential velocity. What's the direction of its tangential velocity? Clearly, the direction of the tangential velocity would be like this. And the tangential velocity is always r omega. So v3 would be I hat v minus j hat, because the tangential velocity is in the negative j direction. V tangential. So that's going to be I hat v minus j hat r omega. And this cannot be simplified any further. So that's what it is. Now, the most important example for our purposes, for what comes next, is the velocity of the 6 o'clock point. So let's calculate that. Velocity of the 6 o'clock point would be, so the 6 o'clock point has, again, same thing. It's got two velocities. One is the velocity that it has from its motion as a whole. So that's the velocity of the center of mass. And the other is its tangential velocity. Now, if the disk is spinning clockwise, what is the direction of its tangential velocity? The answer is it's backwards, right? So the tangential velocity will be in this direction. And so you can write the velocity vector for the 6 o'clock point as follows. It will be I hat v minus I hat v tangential. So that's I hat v minus r omega. And that's the velocity of the 6 o'clock point. The velocity of the 4 o'clock point, which I've marked optional on the slide, is very similar. You can just figure it out yourself. Okay. All right. So now let's look at rolling without slipping. So hopefully you have a clear idea of what rolling without slipping is. So that is the case when some disk or wheel or sphere, anything that can roll, is rolling along the ground, but there is no slipping or sliding between the bottom of the object and the ground, right? So that is the most common type of rolling that you see. If you just roll a ball, it will roll without slipping, unless the ground is extremely slippery, in which case it might slide against the ground for a while before it catches and then starts rolling without slipping. So rolling without slipping is when the point at the bottom of the object is momentarily at rest relative to the ground. So the only type of friction is static friction. There is no kinetic friction. Kinetic friction only happens when the two surfaces are moving relative to each other and there is sliding between the surfaces. One of them is sliding or slipping against the other. So rolling without slipping is when there is no kinetic friction and the point at the bottom, the point in contact with the ground, remains at rest, remains momentarily at rest. Okay, so what is the velocity? Suppose this object is rolling with angular velocity omega and the center of mass of the object is moving with a velocity vcm. The radius of the object, let's say, is r. In general, what is the velocity of the bottom point of this object? That is exactly what we just calculated. In our clock, the bottom point was the 6 o'clock point, and the velocity of the bottom point was v minus r omega. The magnitude of the velocity was v minus r omega. So v in this case is vcm, as it was in the case of the clock. We just called it v in that example. So the velocity of the bottom point, or I should say the velocity of the point in contact with the ground what we just calculated earlier, and that's VCM minus R omega, right? Now, we just mentioned how the definition of rolling without slipping is that the velocity of the point in contact with the ground has to be zero. So we conclude that VCM minus R omega is equal to zero. And so from there, we immediately get the very important condition for rolling without slipping. VCM is equal to R omega. Remember that this is only true when the object is rolling without slipping. Now, I'll just point out one other thing here. This formula that we just derived for rolling without slipping has a superficial similarity to a formula that we had seen in chapter 9, which was the tangential velocity formula. V tangential equals R omega. This formula was used in deriving the VCM equals R omega formula, but they're completely different formulas because V tangential and V center of mass are not the same thing at all. So what is this VCM equals R omega telling us? It's telling us that when an object is rolling without slipping, like this wheel that I have here, if it really is rolling without slipping, then there is a relationship between the rate at which it's rotating, omega, and how fast it's moving. There's a definite relationship between those two, and that relationship is velocity of the center of mass equals radius multiplied by the angular velocity of rotation of that object. Okay, so this is going to be an extremely important formula for the next couple of slides. And please remember that this formula only applies when the object is rolling without slipping. It's not generally true. All right, so let's look at an example problem. So let's look at this example. So see if you can figure this one out. This would have been a top hat question in class. See if you can figure this one out, and if not, you can, and after you've come up with an answer, you can look at how I approach it. Okay, so you've got a solid sphere that's rolling without slipping on a horizontal surface. You're considering 3 points on the sphere. Point A is at the center. O is the center, sorry. A is directly above the center, and B is the point at the bottom in touch with the ground. Okay, you're given the speed of O. So that's the velocity of the center of mass, obviously, and we're calling that V. So the question is, what is the speed of point A and what is the speed of point B? The correct answer is the speed of point B is 0. Can you tell me why? The reason is because we are told that it's rolling without slipping. And the definition of rolling without slipping is that the velocity of the point that's in touch, momentarily in touch with the ground, is 0. And that's why there is no slipping or sliding, because the point that's in touch with the ground at that moment is at rest. So velocity of the bottom point is 0. Vp is equal to 0. What about Va? So to find the velocity of the point A, what we are going to do is we will use the relationship that we had derived earlier. So just think about it. Think about that problem with the clock. The velocity at A is basically the velocity of the 12 o'clock point, right? We've already derived that. The velocity of the 12 o'clock point was V plus R omega. So it's velocity of the center of mass plus R omega, which is in this case, it's just V plus r omega, right? But we do know something about r omega. We know that v center of mass is also equal to r omega, and that is because we are told that it's rolling without slipping. So from here you can see that um, you can get rid of you can replace r omega by v or vcm. They mean the same thing here. So v plus v. So this is 2v. So that means a point at the top will have a velocity twice as a point at the top will be moving twice as fast as a point at the center, and a point in touch with the ground would have zero velocity. So note that we are only talking about instantaneous velocities, right? The point that's in touch with the ground right now, the next moment it would be up somewhere over here, and then it will have some velocity. But at the moment that it's touching the ground, its velocity is zero, just for that moment. Okay, all right. So I would recommend that you try the example on slide 22 yourself. It's fully worked out on the slide. Okay, there is a very important relationship which we are going to just state without proof. We are not going to get into the proof of that. The proof of that is beyond the scope of this elementary course, but it's a very beautiful proof. If any of you major in physics, you might encounter it. Suppose you have some object that is executing some complicated motion. So suppose you have like this rectangular object. You've thrown this object and it might be spinning, and at the same time it might be moving along. You can prove that the kinetic energy of this object can be written, no matter how complicated its motion is. Its kinetic energy would be K is equal to it. There will be two parts to its kinetic energy. One is the kinetic energy due to translation. So let's say that this is the center of mass of the object, and the center of mass is moving with velocity vcm. The kinetic energy would be half m vcm square plus a half I omega square. What is this I? The I is the moment of inertia of the object relative to its center of mass. So half ICM omega square. And that would be, and omega is the angular velocity with which the object is rotating about its center of mass. So the formula for the total kinetic energy of an object that's executing translational and rotational motion, the kinetic energy has two parts. One is the translational part, that's due to translation, and that is exactly what you would expect for a point mass moving of mass m moving with velocity vcm. So it's half m vcm square. And then you have a part that is due to rotation. So this is called translational Ke, and this is called rotational Ke. And the I that you use for rotational kinetic energy is the moment of inertia about an axis which is passing through the center of mass of the object. And omega is the angular velocity with which the object is rotating about its about that axis through the center of mass. Let's look at one example of that. Suppose you have I think I have a very similar example on the next slide. I'll let you try that on your own, but I'm just going to make another one up. So suppose you have a disk of mass m, radius r, and let's say that disk is rolling along the ground. It's rolling without slipping, and its velocity of its center of mass is vcm. So if you're following the center of this disk, it's moving with velocity vcm. The question is, what is the kinetic energy of the disk? So the kinetic energy of the disk would have a translational part and a rotational part. The translational part is just half m VCM square, so that's easy, we already have that. The rotational part would be half I about an axis passing through the center of mass of the disk, so that would mean an axis parallel to the disk, axis perpendicular to the disk passing through the center of the disk. So ICM omega square, right? So let's work out the second term here. There's nothing to do with the first term. 1/2 mVCM square plus 1/2 ICM for a disk is half mr squared. What about omega? So omega is the rate at which the disk is spinning about its center of mass, right? We are given one piece of information which allows us to figure out what the omega is, which is that the disk is rolling without slipping. Now that we could not have used that equation if the disk was not rolling without slipping. In that case, the answer would just be 1/2 I omega squared. There's not much there's no connection between VCM and omega. But if the disk is rolling without slipping, there's an extra relationship that we can use. What is that relationship? VCM equals R omega. So we can plug that in over here and we can write, and then we can just simplify a little bit. So omega is VCM divided by R square, and now we can just simplify this. 1/2 m VCM square plus 1/4 mr square VCM square divided by R square. The R squares cancel out, and then this becomes 1/2 plus 1/4 is 3/4 m VCM square is the kinetic energy of this disk as it's rolling. Okay. Oh, it seems like this is exactly what the problem was on the next slide. So I thought this slide was a sphere, but anyway, so I ended up working this out. All right, so now we're going to look at a few problems that involve rolling and friction. You will see that in many of these problems, it's not immediately obvious what the direction of the friction force is going to be. In some problems, it might be obvious that the friction is in a certain direction, but it might not be immediately obvious what the direction of the friction is. However, there's nothing to be worried about regarding that, because if you just set up the problem and apply Newton's second law and work through it, the math will just tell you what the correct direction of friction is. So there's no reason to be worried that you can't figure out intuitively what the direction of friction is. Okay, so I'll give you some examples of that, and so you will see how that works. But how do you do these problems? It's just a matter of applying Newton's second law. So the workflow is pretty much identical to what we learned in chapters 4 and 5. So you choose your system, you choose sign conventions, and when you're choosing sign conventions, you have to choose them for translational motion, which is what we did in chapter 4 and 5. And you also have to choose them for rotational motion, which means you have to choose either counterclockwise is positive or clockwise is positive. And then you set up F net equals mass times acceleration for all the forces, and tau net equals I alpha for all the torques. And that gives you enough information, enough equations to solve for whatever you need to solve for. One more equation which often comes in handy is that in most of these problems you're told that the system is rolling without slipping, right? So you have some wheel or disc or sphere, and you're told that it's rolling without slipping. You know that there is this very important equation which applies to objects that are rolling without slipping, the equation that connects the velocity of the center of mass of the object with the angular velocity of the object. So VCM equals R omega. And another equation which immediately follows from that, and you can just see that it's immediately going to follow from that. Let's start with VCM equals R omega. If you just take a derivative of both sides of this equation, R is a constant, so the derivative will just apply to omega. So what is dVCM dt? It's just going to be the acceleration of the center of mass. and that is going to be r. And what is d omega dt? Is just going to be alpha. So if an object is rolling without slipping, this condition is important for the next two equations. So if this condition is true, the object is rolling without slipping, then you have VCM equals R omega and ACM equals R alpha. One other thing is, when you're doing problems that involve rolling without slipping, don't forget about friction. Often students will set up all the forces but will just not set up friction. Friction is essential for an object to roll without slipping. If you have a surface which is completely frictionless, and then you pull this disk along, the disk would not have any reason to roll. It would just be purely translational motion. So the fact that it's rolling without slipping means that there has to be friction. All right, so don't forget about friction. So let's look at an example problem. So I'll let you take a look at this example and see if you can figure it out. And let's give it a try. So what we have here is a cylinder, and you have a rope that goes over the cylinder, that's wrapped around the cylinder and goes over the cylinder like this, comes out like this. You're exerting a 50 Newton force at the end of this rope. Right? So I'll just call this force F. Okay, and I'll draw the ground. So you have to find the magnitude and direction of the friction force and also the acceleration of the center of mass of the cylinder. So these are the two things that you need to find out: the acceleration of the center of mass of the cylinder and the magnitude and direction of the friction. All right? Okay, so now let's see how we would do this. Our system is obviously the cylinder. What are the forces acting on the system? So I have the force of friction acting in this direction. I also have, I have the external force acting through the rope. There is also a force of friction, but right now it's not obvious to me what direction the force of friction is. Is it to the right? Is it to the left? I'm not sure. That is what I meant when I was discussing the last slide, that it's not obvious what the direction of friction would be when an object is rolling without slipping. Right? I mean, I don't have a immediately intuitive way of seeing what the direction of the friction is. Of course, there is a way of figuring out what the direction of friction is, and it would be like this. So one way of thinking about it is that what would happen if you did not have any friction on this cylinder? I mean, on the ground. Suppose the ground was completely frictionless and you're pulling on the rope. So what would happen in that case? In that case, the cylinder would start to rotate like this, because there is absolutely no friction on the ground, right? And so the cylinder would just rotate in place. That's what would happen if the ground was completely frictionless. But what's actually happening is that the cylinder rolls forward, right? So something must be preventing the cylinder from rotating in the clockwise direction, and that must be the friction force. And so the friction force acts in this direction. And so if you ask me to intuitively explain why the friction is to the right, that is what I would tell you. But there is no harm if you can't figure that out intuitively. In fact, you don't have to bother to figure it out intuitively. You can just make any choice you want for the friction force, and the math will just set you right in the end. The math will tell you whether your choice was correct or not. Okay? So I'm going to do this problem in which I'm going to make the correct choice for the friction, and we'll see what happens. Okay? So I have my two forces. I have the external force and the friction force, and let's just say that I made a guess that the friction force is to the right. So forget about my justification about why it's to the right. Let's just assume that I guessed it, right? Okay, now let's apply Newton's second law. So we have our forces. We need a sign convention. So we can just choose right is positive. Our sign convention is right is positive. We also need an angular sign convention. So if we have chosen right is positive, if the wheel rotates to the right, it's going to rotate in the clockwise direction. So we should also choose clockwise is positive as our sign convention for angular quantities. All right, so now all we have to do is just set up our torques, set up our forces and torques and write down Newton's second law. So F net equals mass times acceleration. What does that give us? The net force would be capital F plus little f. Both of them are to the right, and so they get positive signs, is equal to the mass of the cylinder, let's just call that m, times the acceleration of the center of mass of the cylinder, right? That is Newton's second law applied to the cylinder, right? Now, this equation is not enough because there are two unknowns, a center of mass and friction. And so the linear form of Newton's second law has just given us one equation. And so that's not enough. We need one more equation. That second equation will come from the rotational form of Newton's second law, which says that the net torque equals I times alpha, right? So what is the net torque going to be? So there are two forces. So both of these forces have torques. Let's draw these two radii, right? So what is the torque of F? So for that, you can just use force multiplied by lever arm. The lever arm is clearly R, right? So the torque due to F would be F times R. And is that a clockwise torque or a counterclockwise torque? To answer that question, just ask yourself which way is the force F trying to rotate the cylinder? The answer is that it's trying to rotate the cylinder in the clockwise direction. So R times F is a clockwise torque and should get a positive sign. Okay, now what about the torque due to little f? So about the center, the torque due to little f is just going to be little f multiplied by the lever arm, which again is R. So now the question is that a clockwise or a counterclockwise torque? The answer is it is a counterclockwise torque, because by itself the force little f is trying to rotate the system in the counterclockwise direction. It's trying to rotate the cylinder in the counterclockwise direction. So minus f times little f times r is our net torque. That is equal to I alpha. I in this case is 1/2 m r square for a cylinder. That's just out of the table. Times alpha. Now what do I do with alpha? So we saw in the last slide that when an object is rolling without slipping, you have the equation VCM is equal to R omega. And if you take a derivative of that equation, ACM is equal to R alpha is what you get, right? So I can get rid of alpha from this equation. I can write it as ACM divided by R. And so let's clean up this equation and see what we get. So F minus little f is equal to, I'm mixing up the m's, I should use the same m. F minus little f is equal to, if you divide both sides by r, then you have an r square downstairs, which cancels the r squares upstairs. And so you get 1/2 m ACM. And that's the second equation, connecting our two unknowns, F and ACM. So now if you want to solve these equations, the easiest way to solve them, so this is our equation number 1, and this is our equation number 2. The easiest way to solve them would be to just add up the two equations. So 2F is equal to MACM plus half MACM is 3/2 MACM. Yes. And so capital F. So from here we can easily solve for ACM. It's just going to be 4F divided by 3M. That's the acceleration of the center of mass of the cylinder. Notice that this quantity will be positive, and so the math is telling us that the cylinder accelerates to the right, which is exactly what we would expect. Okay, now let's calculate the friction force. So to calculate the friction force, I just have to plug in this ACM that I got into either of my equations 1 or 2. So let's plug it into equation 1 maybe. So F plus little f is equal to m times 4f divided by 3m. The m cancels out. So little f is equal to 4/3 f minus f, which is f divided by 3. Notice that little f came out to be positive. The fact that little f turns out to be positive means that we guessed the direction of friction correctly. So I told you that in the end, the math would set you right if you had made the wrong choice regarding the direction of friction. So in this case, we had guessed the friction to be to the right. We got a positive answer for the friction when we solved for it, and that is the math telling us that we had chosen the correct direction for friction. Suppose I had set up all my equations with little f pointing to the left. You can try this yourself. Everything would work out very similar. You would get the same magnitudes for friction, but you would get a negative sign. The negative sign is just the math telling you that you have made the wrong choice for the direction of the friction. So all you have to do is go back to your original diagram and flip the direction of the friction. Okay. So in the next slide, I have a very similar problem, and you can actually see my sick Microsoft Paint skills, because you can see that I started with this diagram and I turned it into this diagram. So you can again work through this, and in this case try to guess the direction of friction. In this case, the correct answer is friction will actually point backwards in this particular problem, and I'll let you work it out yourself. If you want, you can just start with the wrong answer. You can just pretend that friction points to the right, like in the problem that we just did. If you work it out carefully, you will see that you get a negative answer for the magnitude of friction, and that's just the math telling you that you have chosen the wrong direction. And if you do the same problem with the friction pointing backwards, you will get the same result for friction, but it will turn out to be positive. So the math is telling you that you chose the direction correctly. So that's all there is to these kinds of problems. I have a slightly harder problem over here, but it doesn't really involve, in the optional slide, it doesn't really involve anything new. It's just a little more tedious than the other two that we did. So this problem is marked optional, but you can try it if you want. Like, there's nothing that in that problem that you don't, that we haven't discussed. Okay. The next thing that we'll very briefly mention is rotational work and power. So you know that in one dimension, work is given by integral f dx in one dimension. You can write a very analogous formula for work done by a torque, and it's just tau d theta. Remember that x is kind of analogous to theta, and f is analogous to torque. So you can just write this down just from analogy, right? And rotational power is just d. So you can write dw is equal to tau d theta, That is the work done when you have a torque acting and it just rotates a system by a tiny amount d theta. And the power is simply the rate at which work is done. So that's dw dt, and that's tau times d theta dt. D theta dt, as you know, is d omega, is omega. So you have this formula: power is equal to tau times omega. This formula is very analogous to the formula that you saw in chapter 6 and 7, where power was force multiplied by velocity. So this is torque multiplied by angular velocity. Okay, I have a plug and chug problem on slide 30, and that pretty much concludes our discussion of Newton's second law in rotational form. Okay, the last topic in this chapter is angular momentum. So what is angular momentum? Angular momentum is a very fascinating subject, and when I'm teaching this in class, I often say that if I start talking about angular momentum, I could just go on talking till the end of the semester. So it's a very fascinating subject. It has a lot of applications, but for the purposes of this course, and it breaks my heart to do this, but for the purposes of this course, I'm just going to take this really beautiful subject and break it down into 4 bullet points for you, and which is all that you need to know in order to do problems. Okay, so let's first start with bullet point number 1. So the topic is angular momentum. The first thing that you need to know is the angular momentum for a point mass, right? Or an extended object that's being treated as a point mass. So suppose you have a point mass that's moving with some velocity v, right? So the point mass has mass m and it's moving with some velocity v. So you know what its linear momentum is from chapter 8. Its linear momentum is p, and p is defined as mv, right? Okay, now let's say that this point is your observation point q, right? So I'm just arbitrarily naming this point. So this is where you're observing the particle from, right? What is the position vector of the particle? The position vector of the particle is r. So r is a vector which tells you where the particle is. Okay, the angular momentum of the particle relative to the point q, and angular momentum is a vector, is defined as r cross p. That is the definition of the angular momentum. Using the cross product formula, you can find the direction of the angular momentum vector. You can see the direction of r, you can see the direction of p. So to find the direction of the angular momentum vector, you take the fingers of your right hand, point them in the direction of r, curl them towards the direction of p, and your thumb will be pointed into the board. So the direction of the angular momentum vector in this case is into the board. Into the page or into the board. Okay, now you know the direction, you have the direction clear. So let's just focus on the magnitude of the angular momentum vector. You know the magnitude of a cross product is just magnitude of r, magnitude of p, sine of the angle between r and p. The angle between r and p clearly is this angle. So I'll just write the p over here. The angle between r and p is this angle. So the magnitude of the angular momentum vector is rp sine theta. And just like we did in the case of torque, you can write this as r sine theta multiplied by p. R sine theta, so I'll just write this as r sine theta multiplied by p. R sine theta might ring a bell from earlier on in this chapter. It's just the lever arm of the momentum vector. And you should remember how to calculate the lever arm of a vector. So what you do is you draw a line through the vector, which is so the momentum vector in this case, and then you make a perpendicular from that line, from the reference point out to that line. This perpendicular is called the lever arm, right? And geometrically you can see that it's just r sine theta. So an easy way of calculating the angular momentum is to just use the lever arm if the lever arm is obvious. So if in a certain problem the lever arm seems obvious, you can just use that to calculate, do lever arm multiplied by linear momentum to get the angular momentum. Now, one interesting thing about angular momentum is the following. It totally depends on where you're measuring it from. So you might have noticed that I have the q subscript everywhere when I'm calculating the angular momentum. So you might have wondered, why am I writing L sub q? Why am I specifying the point where I'm measuring the angular momentum from? The reason is the angular momentum totally depends on where you're measuring it from. So suppose I had chosen to measure the angular momentum from this point, right here, okay? So let's just, since this diagram is getting cluttered, so let's just draw another one. So I have the same particle moving with linear momentum p, but I'm measuring it from the point S, which is, suppose it's over here. It's in the same line, same straight line as p, as the linear momentum vector. So what is the angular momentum of the particle relative to S? The answer is, what's the r vector? What's the position vector of the particle from S? The position vector is this one, right? What is r cross p going to be? So r and p are in the same direction. So r cross p would be r multiplied by p multiplied by sine of the angle between r and p, which is 0. Sine of 0 is 0. So ls is just going to be 0. So the angular momentum of the particle relative to the point S is 0. So you can see that the angular momentum depends, is very much dependent on where you're measuring it from. Okay, now let's move on. So that's how you get the angular momentum of a point mass, or something that can be, you might have an extended object, but let's say that you're treating that extended object as a point mass. So in that case, you can apply this formula. Okay, now let's move on to the angular momentum of an extended object or rigid body that's rotating about an axis of symmetry. So one example could be a sphere. So I'm drawing this as a circle, but this is a sphere that's rotating about an axis which passes through its center. The sphere is rotating like that. So that's an example of an extended object that's rotating about a symmetry axis. Another example would be, let's say you've got this disk plate and it's rotating about an axis which passes through the center of the disk. It's rotating like this maybe. So that's also another example of extended object that's rotating about an axis of symmetry. So in this case, the angular momentum is going to be I, which is the rotational inertia of the object about the axis of symmetry, multiplied by omega. Omega is the angular velocity of rotation, right? Now, this formula is quite similar to the, it is analogous to the formula for linear momentum. Remember, linear momentum is mass multiplied by velocity. Mass measures inertia. In the rotational world, what is the analog of mass? It's I, and what is the analog of velocity? It's omega. So L equals I omega is analogous to the formula for angular momentum, for linear momentum. Okay, so this is how you calculate the angular momentum of an object that's spinning about an axis of symmetry. And as such, this particular angular momentum is called the spin angular momentum. Okay, now do you think this angular momentum depends on where you're measuring it from? So, like the last angular momentum, like the uh, if I measure the omega from over here, or if I measure the omega from over here, is it going to be is my answer going to be different? Uh, the and really strange answer to my question is that it the spin angular momentum does not depend on where you're measuring it from, and the proof of that is very beautiful. But we are not going to get into it. Obviously, it's a bit too advanced for this course. But you can prove that the spin angular momentum does not depend on where you're measuring the angular momentum from, even though this formula ultimately comes from L is equal to R cross P. So you take L is equal to R cross P and then you calculate the angular momentum of the extended object and you get this formula L equals I omega. Even though L equals R cross P does depend on where you're measuring R and P from, L equals I omega does not depend on where you're measuring it from. So spin angular momentum is an intrinsic property of a rotating object. These facts have really beautiful and profound significances when you go deep into quantum mechanics and stuff like that. But we're really not going to get into any of that stuff here. So all that you need to know is how do you calculate the angular momentum of an object that's rotating about an axis of symmetry. All right. Next fact. We had seen from in chapter 8 that, okay, so let me remind you of something from chapter 8. We had seen that the net external force is equal to the rate of change of total linear momentum of the system, right? And from here, we had seen that if the net external force is zero, which means all the external forces cancel out or there is no external force at all. If this result on the left side is zero, then dp dt is equal to zero. So if F external is equal to zero, that would mean dp dt is equal to zero. And so P would be conserved. And this was called the conservation of linear momentum. And I told you that this is a fundamental law of the universe. There is there is something very, very similar with angular momentum. So you can prove that the net external torque on a system is equal to the rate of change of angular momentum of the system. And in fact, this equation that I just wrote down is our bullet point number 3. So the net external torque on a system is equal to, and I could probably just write this as the net torque on a system is equal to the rate of change of angular momentum of the system, right? And it immediately has this corollary that if, just like the left side, if the net external torque is zero, uh, then dl dt is equal to zero, and so L will be conserved. And this is our bullet point number 4, that angular momentum is conserved if the net external torque on a system is zero. So this would be our bullet point number 3, and this would be our bullet point number 4. So this is called the law of conservation of angular momentum. Angular momentum. Which says, just to repeat myself, that in the absence of an external unbalanced torque, the total angular momentum of a system is conserved. All right, so now we're going to look at some examples of problems on angular momentum. So let's start with this example. I'll let you take a look at this first and see if you can set it up, and then let's discuss it. Okay, so in this example, you've got A and B, and A throws an object of mass m to B. B is a little bit lower. And they're on the balconies of two high-rise buildings. Okay, and so the object is falling vertically under B. Okay, so the question is, okay, so you're given this distance, the distance between the buildings. This distance is d, and you're given the mass of the object, that's m, and okay. So what is the object's angular momentum after t seconds relative to A and B? All right. So the angular, so the object is falling vertically. Let's say that its velocity happens to be v. And so it has a certain momentum, and its momentum, let's say, is p, right? It's going to be in the downward direction. P is obviously equal to mass times velocity. Okay, so let's calculate its angular momentum relative to b. So obviously its angular momentum relative to b is going to be 0, as we saw when we were discussing angular momentum r cross p. So angular momentum relative to b, probably use a different color. Angular momentum relative to b is going to be r cross p. The r as measured from b is this distance. That's r. And so r cross p is obviously going to be 0 because the two vectors point in the same direction. So there is no angular momentum as measured by b. What about the angular momentum as measured by a? So for that, you could use r cross p. R would be this vector. But is there an easier way of doing it? That would be our r. The easier way would be to use the formula that it's p multiplied by the lever arm of p, right? So what is the lever arm of p? So to find the lever arm of p, you would draw a line through the vector p. The line would go like this. And then you would make a perpendicular through from the reference point out to that line. So that perpendicular would look like this. And this would be the lever arm of the momentum vector. We do know what this lever arm is, and so that's why this method is much easier. So the lever arm is simply equal to d. So d multiplied by p, which is mv, is the momentum as measured by a, angular momentum as measured by a. Now v is not given in the problem, but we know that its initial vertical velocity was 0, and its acceleration is just g, acceleration due to gravity. So v from the kinematic equations is just g multiplied by t. So this is just going to be equal to dm gt. That's the angular momentum as measured by A, right? Okay, now, so that answers the first part. Now, the second part is asking, what is the torque measured by A? Now, torque is force multiplied by lever arm, right? The only force on the falling object is the force of gravity, which is mg, right? So the torque would be mg, and mg would have the same arrow in the downward direction, just like P. I'm not drawing it because it would just make the diagram more cluttered. So what is the torque of mg relative to the point A? So again, you would just draw um, a line through the mg vector, and it would just be the look very similar to what we have with the p vector, right? And then the lever arm would just be d. So the torque as measured by A is just going to be the force, which is mg. So all I'm doing is force times lever arm. So the lever arm is d and the force is mg. So the torque is just going to be mg multiplied by d, right? Now we can check one thing over here. Relative to the same reference point, we always have this equation that the torque is equal to the rate of change of angular momentum. That's what we showed just a little while ago. So the net torque is equal to the rate of change of angular momentum over here. Let's check if that equation works out. So if you take a derivative of LA, so that will just be dmg, which is just exactly equal to the torque. So it is true that torque is equal to dl dt in this example, and they're both measured relative to the point A. All right, so let's calculate the angular momentum of a point mass m moving in a circle of radius r with speed v. Okay, so how do we do this? We've seen that there are two formulas for angular momentum. One is linear momentum multiplied by the lever arm, r perpendicular times p, which is the same as rp sine theta. And then there is also L is equal to I omega. So which one do we use here? It turns out that for a point mass, you can use either one, right? And I'll show you that both of these give you the same answer. So if the object is moving with the speed v, it has a linear momentum p, which is equal to mv, right? So what would the angular momentum be? So if you use the formula L is equal to r perpendicular multiplied by p, r perpendicular is just r, right? So the angular momentum turns out to be r multiplied by p, which is r mv times r. And if you use I omega, let's try that. So what is the I of a point mass? So I of a point mass, so L is equal to I omega is what we are doing. I of a point mass is mr square, and omega is v divided by r. So if you simplify this, you get mvr, same thing. So for a point mass, you can use either of these formulas. But if it's an extended object, for a point mass moving in a circle, you can use either of these formulas. But if it's an extended object, then you have that's spinning about an axis, then you have to use I omega for that. And if it's a point mass moving in a straight line, you use r perpendicular times p. So just to summarize, calculating angular momentum for the examples that you're going to see. So if you have a point mass moving in a straight line, then you want to do L is equal to r perpendicular times p, or rp sine theta, which is the same thing as rp sine theta. So, and then if you have an extended object rotating about a symmetry axis, then you use L is equal to I omega. And if you have a point mass moving in a circle, then you can use either one. So either R per, then you use either one. You get the same answer. Okay, so let's look at an example from the PowerPoint. This one. So I'll let you read this problem for a moment. Feel free to pause the video, and then let's think about this problem. So in this problem, what's happening is you have a rod which is pivoted around one end and it's hanging vertically. The length of the rod is L and the mass of the rod is M. You take a piece of putty and you shoot it at the rod, and it sticks to the bottom of the rod. Let's make this a little larger. Sticks to the bottom of the rod, and the whole thing starts rotating. The first thing that you need to find is the angular velocity of the rod immediately after the collision. So you have to find the omega the moment it hits the bottom of the rod. And the second thing you have to find is how high does the end of the rod rise. Okay. All right, so let's focus on the first part. So for the first part, we can use conservation of angular momentum. So remember that conservation of angular momentum applies when the net torque of a system about a certain reference point is 0. When the net torque is equal to 0, L is conserved. Generally, if a system has a natural pivot point around which it's rotating, and you calculate all the torques and angular momenta relative to that pivot point, then the net torque will be 0 and angular momentum will be conserved. So the point of this is that if the system has a natural pivot point, that's a very good point to choose as your reference point, because the angular momentum is going to be conserved about that point, right? So we're going to choose the pivot point over here, let's call it O, as our reference point for calculating angular momentum. And if we do that, we can be sure that the angular momentum is going to be conserved about that point, because the net torque about that point would be 0. Okay, so let's go ahead and calculate the angular momentum. So we're going to do a calculation very similar to our conservation of momentum calculations. We're going to set the total angular momentum before equals the total angular momentum after the collision. So before the collision, it was only the point mass that was moving that had angular momentum. What is the angular momentum of this point mass? So this is a point mass moving in a straight line. So its angular momentum can be found from r perpendicular multiplied by p. So p is the momentum of this point mass, which it's going to be mv, and r perpendicular would be this distance. So you draw a line through the momentum vector, make a perpendicular from the reference point to that line, and the length of that perpendicular is the lever arm, or r perpendicular. Clearly, that's just going to be equal to L. So the angular momentum of the point mass before the collision is just going to be mv multiplied by L. Now, once the point mass gets stuck at the bottom of the rod, and both the point mass and the rod start rotating, we can then both of the point mass and the rod have angular momentum, right? So for that, you use the formula I times omega. So what is the I of this whole system? It would be the I of the rod plus the I of a point mass that's going in a circle. So the I of this rod is going to be 1/3 ml squared, and the I of a point mass going in a circle is just going to be little m L square. And so that's the total I of the system times omega will give you the angular momentum of the system, right? And so now we can just solve for omega. So omega is going to be mvl divided by 1/3 capital M L square plus M L square. And you could probably simplify that a little bit. Okay. And why did I use 1/3 ml square? And that is because that is the I for a rod that's rotating around one end. So that's so that we saw earlier in chapter 9, I think, that turns out to be 1/3 ml square. Okay, so that is your omega. Now let's try the second half of the problem. Second part says that how high does the end of the rod rise? So I'll just draw this again. This is the pivot point. The rod was initially like this right after it got struck by the putty, and then it rose up. Now it's like this. This angle is theta. The angle really doesn't matter. Let's say that the height that the rod rises is h. Okay, so we are going to use conservation of energy here. And we are going to, so when we calculate potential energy, the formula for potential energy that we had seen in chapter 7 was mgh, where m was a point mass, right? In this problem, we'll have to calculate the potential energy of the rod. The rod can be treated as a point mass located at its center of mass, right? So instead of thinking of the system as for purpose of calculating potential energy, instead of thinking of the system as a rod and a point mass, you can think of it as a point mass and another point mass located at the center of the rod. So just for the purpose of calculating potential energy, you can think of the rod as a point mass located at its center of mass. Okay, so we know how high the putty rises. Let's call that h, that's unknown. We also need to know how high the center of the rod rises. So this is where the center of the rod was, and this is where it rises up. Can you tell me what this height is going to be? Think about it a little bit. If you think about it carefully, you will realize that this height is actually h divided by 2. And the reasons for that are simple geometry. You can use similar triangles to prove that. So if the end of the rod rises by an amount h, the middle of the rod rises by an amount h divided by 2, right? And that is just because of geometry. All right. You can ask me during office hours if you have a question about how that, why that is h over 2, but that has absolutely nothing to do with physics. It's just a geometrical fact. All right, so keeping that in mind, let us now apply conservation of energy. So the equation for conservation of energy is K initial plus U initial plus W other equals K final plus U final. There is no friction or anything here, so forget about W other. K initial would be the kinetic energy of the system just after the putty struck the rod. So that would be, we could use half I omega square for that. We know the I of the whole thing. I of the whole thing is 1/3 m L square plus little m L square. So half I omega square. We already calculated omega right after the collision in the first part, right? And let's take the, let's calculate the potential energy of both the masses separately. So the potential energy of, and we're going to take h equals 0 over here for the smaller, for the putty, and we're going to take little h is equal to 0 over here for the point mass, the center of mass of the rod, right? So both of these masses were at the zero position of height, so they didn't have any potential energy to start with. Okay, now let's calculate the kinetic energy after the in the final configuration where the rod has risen up to its maximum height. So it's at rest. The whole thing is at rest at that point. So we don't have this kinetic energy over there. We only have potential energy. So the potential energy change for the putty is going to be little m gh. What is the potential energy change for the center of mass of the rod? That is going to be capital M G h over 2. And that is because the center of mass of the rod rises up by a height h over 2. Right? And so now all you have to do is just solve for h, and you have numbers for everything here. So you just need to solve for h, and you'll get the answer. Okay, so that's pretty much how you do problems on angular momentum. The last thing that I'm going to talk about is a few applications, a few practical applications of angular momentum. So the conservation of angular momentum has several fascinating consequences. One consequence is the gyroscopic effect, right? So this device over here is called a gyroscope. Notice this thick disc over here, which is encased inside in all these rings, and this disc is connected to a cylinder, which is the blue cylinder over here, and they can rotate together, right? So typically this disc is set into motion. There's a little blue arrow here showing the omega. I'm just going to get rid of my markings here so you can see. So you can see this blue arrow showing the omega. So that shows you how the disc, how the thick ring rotates together with the cylinder that it's connected to. Now this thick ring has a large moment of inertia. So once you start it rotating, it has a lot of angular momentum, because angular momentum is I times omega. I is large for it, and omega is also large if you set it rotating very fast. So I times omega is going to be pretty large, and so it will have a significant amount of angular momentum. Now, if there is no friction, then there is nothing to change that angular momentum, right? And so the angular momentum will remain conserved because there is no external torque on that system, right? So if the angular momentum is conserved, remember that angular momentum is a vector. So a vector being conserved means its magnitude is conserved and its direction is conserved, right? So since the direction of the vector is conserved, this ring and the cylinder at the center of it will always, while it's spinning, it will always want to point in the same direction, right? So that is very, very useful, because this cylinder, this ring and the central cylinder uh, are gimbaled, and so the rest of the apparatus can rotate, but these can continue pointing in the same direction. So as you can see in this diagram over here. So once you set this central disk to rotate, it will always keep pointing in the same direction. So as you can see, it's pointing in the same direction, pointing in one direction over here, and it's pointing in the same direction over here, even though the rest of the apparatus has been rotated, right? So what do you think is a use for this? So one very important use for this is that it can be used in navigation. So you point it in a certain direction and set it rotating, and then it will always point in that direction, even though the rest of the apparatus can change its orientation. So this is very, very useful in ships and planes. Now, ships and planes use gyroscopes a lot to ensure to uh, keep track of which is the correct direction, because when you're in a plane, it's very difficult to every direction looks the same. So or if you're out in the ocean, then every direction looks the same. So a gyroscope can be used to keep your bearings. Okay, another application of this is when you pitch. I always forget what sport this is. I assume this is a football. So when you pitch a football, if you give it a spin, then the football will keep pointing in the direction of its spin. So in this case, this football has been given a spin indicated by this curved arrow here, omega, and so it will keep. It will have an angular momentum which points in the direction uh, uh, shown by this arrow. Now, let me just mention one other thing here, which I don't remember if I mentioned earlier. Suppose an object is rotating. Suppose you have a sphere that's rotating around this axis. Actually, let's use this. Let's use a different example. Suppose you have a disk that's rotating about an axis which comes out of the page. And it's rotating in this direction, right? So the angular momentum L was I times omega. So from this formula, you can see that L will have the same direction as omega. As long as I happens to be an axis of symmetry, you have this formula. So L is equal to I times omega. And you know how to find the direction of omega, right? Using the right-hand rule. We talked about that back in chapter 9. So how do you use the right-hand rule to find the direction of omega? You curl the fingers of your right hand in the direction of rotation, and your thumb points in the direction of omega. So the same thing applies for L as well, because L and omega will have the same direction. So you can use the right hand rule to find the direction of the angular momentum. Okay, so that is why for the gyroscope, if the gyroscope, now you can understand why the direction of the angular momentum vector is the way it is for both the gyroscope and the football. Okay, another application, similar application, is bullets. So when a gun fires a bullet, typically you would want the bullet to maintain a particular orientation. You don't want to be flacking around. So how do you make the bullet keep pointing in the same direction as it's flying through the air? The barrel of a gun is grooved. And so the spiral grooving inside the barrel of a gun causes the bullet to spin while it's moving through the barrel of the gun. And so by the time it emerges from the barrel of the gun, it has a pretty high spin. So it has a large angular momentum. And so since the external torque on it due to friction, air resistance, is very, very small, the angular momentum of the bullet is essentially conserved. And so its angular momentum vector keeps pointing in the same direction, and the bullet maintains its orientation. Okay, now there are many, many applications of gyroscopes. I mentioned navigation, ships and planes, but there are many other applications as well. One other application is that if you are using a camera to take a picture, then you want your camera to be pointing in the same direction. However, if you're walking around while taking the picture, or if you're in a helicopter while you're taking the picture, then there's a chance that your camera will move around a lot, and so the image will not be pleasant to look at because the camera was bumping and jerking and moving around a lot. So in order to always make your camera point in the same direction, you can connect it to a gyroscope. And those are called gyro cameras, and they're used a lot in filming movies. So here's an example of a gyro camera. The camera is connected to is mounted on a helicopter, but as you can see, the helicopter might be moving around, but the camera always points in the same direction. So it's a gyro stabilized camera. Okay, now what is the result of taking a picture with a gyro stabilized camera? Let's take a look at that. So here is a handheld gyro stabilized camera. So on the left side, you can see what happens if you just have a camera which is not stabilized and you're walking along and running the camera. And on the right side, you have a gyro stabilized camera, and you can see the difference in the image when the camera is stabilized. Okay. All right, so that's one class of applications. Another class of applications of angular momentum conservation is the following. L equals I omega. L equals I omega, right? So if L is conserved, I'll just write this again. If L is constant, now for some reason, suppose I changes. Let's say I goes up or goes down. Let's say that I goes down. What must happen to omega if L has to be constant? The answer is that omega has to go up, right? So if the I of a rotating system goes down for some reason, the omega of the rotating system has to increase, which means that it will rotate faster. If the I increases, the omega will go down and it's going to rotate slower. So L is equal to I times omega. Let's look at an example, an application of that. So there's a really nice demonstration which I do in class where I demonstrate, where I show this. Obviously, I can't do that now, but I'll show you a video. Here's an ice skater, and I'll let you watch. So did you see what happened? So she was at first rolling, she was at first spinning slowly, but she had her arms and legs spread out, and so her eye was larger. Remember that more mass distributed away from the axis of rotation gives you a larger eye. So the eye was larger. Then she brought her arms and legs close to her axis of rotation, and that made her eye smaller. So her omega has to go up to conserve angular momentum, and so she started spinning really, really fast. Okay, so that's the second class of applications. The third category of applications of angular momentum is that if you have a composite system and for some reason, suppose, so if you have a system, a complicated system with different parts that can rotate, if the angular momentum of one part of the system changes, but the total angular momentum of the system is conserved, then the angular momentum of the other part of the system must change in a certain way in order to make the total angular momentum zero, right? So what's an example of that? One example of that is a helicopter. So suppose, just imagine a helicopter that's sitting on the ground and it's not rotating. The blades are not rotating. So the helicopter is at rest. Now suppose the blades are turned on and so they start rotating. The rotors start rotating really fast and the helicopter takes off. What was the angular momentum of the helicopter before the rotors were turned on? The answer is zero because everything was at rest. After the rotors are turned on, let's say the rotors are rotating like this. What is the angular momentum of the rotors? Now the rotors have some angular momentum, but the total angular momentum of the system has to be zero, conservation of angular momentum. So something else has to rotate in order to compensate for the fact that the rotor suddenly acquired some angular momentum. What do you think must rotate in the opposite direction to make the total angular momentum zero? The answer is the body of the helicopter. So if the if a if the blades of a helicopter start rotating in one direction, conservation of angular momentum would make the body of the helicopter rotate in the opposite direction. So that would be a problem, obviously, because you don't want the body of the helicopter to rotate while the helicopter is flying. So that is prevented by using a tail rotor. And that is the reason that helicopters have tail rotors. So the tail rotor exerts a torque which prevents the body of the helicopter from rotating uh, in the opposite direction. It's quite possible that so sometimes the tail rotor of a helicopter might get damaged, or in a war situation it might get shot. uh, that's quite fatal for a helicopter, because if its tail rotor is stops working, then the body of the helicopter does start rotating in the opposite direction,